August 3, 1943. Bovington Camp, Dorset, England. A line of tanks idles on the testing grounds, their engines rumbling in the early morning mist. Mechanics clutch clipboards, recording engine temperatures and odometer readings with precise efficiency. The British Army's newest cruiser tank, the Cromwell, sits beside an American M4 Sherman, both prepared for a 2,000-mile reliability trial the War Office has designated Exercise Dracula. In London, officials expect the British-designed Meteor engine to prove superior to the American radial, restoring national prestige after years of imported equipment. But as the convoy begins its journey across England, the numbers will tell a different story. The Cromwell promises 40 miles per hour. The Sherman barely reaches 25. Yet within 6 weeks, one will log less than half the maintenance hours of the other, and a classified report will quietly rewrite Allied tank procurement for the remainder of the war. The road to Bovington began months earlier, in the cramped offices of Britain's Directorate of Tank Design, January 1943, Chertsey, Surrey. Engineers finalized the Cromwell specifications, powered by the 600-horsepower Rolls-Royce Meteor, a ground adaptation of the legendary Merlin aircraft engine. Official Ministry of Supply memoranda described the design as the fastest tank ever conceived. After the North African campaigns, British commanders demand speed. German panzers had outmaneuvered British cruisers repeatedly. The solution? A fast, reliable battle tank, capable of restoring Britain's reputation for engineering excellence. The Cromwell emerges from this pressure 27 tons of steel, mounting a 75mm gun, capable of speeds that would shame any tank in existence. Confidence runs high in the design bureaus. Rolls-Royce engineers boast the Meteor's power will revolutionize armored warfare. Production facilities at Leyland Motors and Birmingham Railway Carriage prepare assembly lines. The War Office schedules demonstration trials and prepares glowing press releases about British technological superiority. Yet beneath the optimism, troubling reports circulate. Early field trials reveal persistent problems, overheating, clutch wear, transmission failures occurring with alarming frequency. Internal memoranda from the Directorate of Mechanical Transport warn that endurance remains unproven under campaign conditions. These concerns stay buried in classified files, while public statements emphasize only the Cromwell's impressive capabilities. Britain builds for speed. America, however, builds something else entirely. While Britain experiments with high performance, the United States perfects industrial repetition. Ordnance officers test the M4 Sherman, documenting not speed records, but reliability statistics that will prove far more valuable. The Sherman's Continental R975 radial engine produces only 400 horsepower, 200 less than the Meteor, yet demonstrates mechanical endurance that impresses even skeptical observers. U.S. Army Ordnance records show Shermans running over 5,000 miles without engine replacement. The emphasis: standardization rather than innovation. 90% parts interchangeability across thousands of tanks. Any mechanic can service any Sherman using standard tools and common spare parts. American Ordnance Report No. 428 from 1943 documents this philosophy with precision. Where British tanks feature hand-fitted components and manufacturer-specific parts, Sherman production demands absolute uniformity. The system values predictability over prestige, reliability over raw performance. The contrast reveals deeper differences. Britain prizes engineering elegance and technical sophistication. America values mass production and logistical efficiency. British tanks emerge from skilled craftsmen in dispersed factories. American tanks roll off centralized assembly lines operating 24 hours daily. One approach seeks to build the perfect tank. The other aims to build enough good tanks to overwhelm any enemy through sheer abundance. When these philosophies meet in August, only one will survive the numbers. The orders that will seal the Cromwell's fate arrive from Major General A. E. Richardson of the Directorate of Mechanical Transport. Exercise Dracula, a secret endurance test comparing British and American tanks under identical conditions. The directive specifies 2,000 miles of mixed terrain, full combat loads, realistic maintenance protocols. 20 Cromwell tanks will compete against 10 Shermans. Crews from the 2nd Royal Tank Regiment. Technical observers from Rolls-Royce and Leyland Motors. War Office Directive No. 2013/43 establishes uncompromising standards. Official briefings predict the Meteor engine will demonstrate superior field performance and validate British design philosophy. Staff officers prepare reports emphasizing expected American shortcomings, slower speed, less powerful armament, inferior cross-country mobility. The exercise is meant to generate evidence for reducing Britain's dependence on American imports. Richardson's final instruction contains language that will prove prophetic. No tank shall be withdrawn until rendered unfit to move under its own power. The general intends this requirement to prevent premature conclusions from minor breakdowns. Instead, it will document the Cromwell's systematic mechanical failures with unforgiving precision. Preparation consumes the summer months. Crews receive intensive training on both tank types. Rolls-Royce engineers install monitoring equipment, temperature gauges, oil pressure sensors, vibration detectors, recording every mechanical stress. The course itself stretches from Bovington through Salisbury Plain, north to Yorkshire, across to the Midlands, and back to Dorset, 2,000 miles, covering every terrain type British tanks might encounter in European operations. By late July, everything stands ready. Fresh paint, full fuel loads, spare parts, tools, maintenance equipment. Observation teams prepare to document every mile, every repair, every moment of downtime. Richardson himself plans to review daily progress reports, confident the trial will vindicate British engineering and justify continued Cromwell production. The convoy departs at dawn on August 3rd. Within hours, the first cracks will appear in Britain's confident predictions. August 3rd through 5th, 1943. The first day seems to confirm every optimistic prediction. Cromwell tanks sprint across open roads and fields at record speeds, their powerful Meteor engines pulling ahead of the steady-paced Shermans with effortless superiority. Observers note impressive acceleration and cross-country performance. Newspaper correspondents file stories praising British engineering ingenuity. But the mechanics tell a different story. Within 4 hours, technical logs begin recording abnormal oil temperatures 210 degrees Fahrenheit on multiple Cromwell tanks, well above recommended operating limits. Clutch wear appears earlier than expected. Rolls-Royce technicians hastily installed temporary cooling measures, adding extra oil lines and modifying fan shrouds. Exercise Dracula Daily Log No. 1 captures these early warning signs with clinical precision. Oil consumption exceeds predictions by 40%. Transmission temperatures run 15 degrees hotter than design specifications. Engine vibration measurements show concerning amplitude at sustained high speeds. To casual observers, the Cromwell looks unstoppable. To engineers reading the instrument data, it's already operating beyond safe margins. The Shermans generate remarkably little concern. Lower-powered engines run cool and steady, maintaining consistent performance without dramatic temperature spikes. American mechanics perform routine checks and find nothing requiring immediate attention. The tortoise and hare dynamic seems obvious, but this race will be decided by mechanical endurance, not strategic cunning. Before the convoy reaches Salisbury Plain on the second day, Tank No. 5's gearbox seizes without warning, grinding halt on an uphill climb. Inspection reveals catastrophic internal damage, metal fragments, contaminating lubricant, bearings worn to failure, gears stripped beyond field repair. Complete gearbox replacement required. 18 hours with factory-trained technicians and specialized tools. The failure shocks Rolls-Royce observers. Predictions suggested such breakdowns might occur after 1,500 miles or more, not after barely 200. Emergency consultations between field teams and Chertsey design offices produce no immediate explanation. The gearbox had been manufactured to exact specifications, properly installed, correctly operated. Yet it failed catastrophically during routine operation. Richardson receives his first concerning report on August 5. While maintaining public confidence, private correspondence reveals growing unease. The general requests detailed analysis of Tank No. 5's failure and orders enhanced monitoring of all remaining Cromwell tanks. If this represents a systematic design flaw rather than isolated manufacturing defect, the implications will prove devastating. Within 200 miles, pride begins to crack under mechanical strain. The second week transforms isolated concerns into undeniable crisis. By August 10, 11 of 20 Cromwell tanks require significant mechanical intervention, a 55% failure rate that shatters all predictions. Field maintenance teams work around the clock, replacing gaskets, adjusting transmissions, performing emergency repairs that should not be necessary on nearly new equipment. The statistics grow worse with each passing day. 11 Cromwell tanks under repair, 0 Shermans out of action. Average British maintenance time, 4.2 minutes per mile. American maintenance time, 1.8 minutes per mile. Directorate of Mechanical Transport maintenance logs record brutal details. Cromwell tanks suffer persistent oil leaks from inadequate gasket materials. Clutch assemblies wear rapidly under the Meteor's tremendous torque. Transmission components fail repeatedly despite field replacements. The power that gives the Cromwell its impressive speed is literally tearing the tank apart from within. The Sherman's consistency proves equally remarkable in the opposite direction. American tanks maintain steady performance, requiring only routine maintenance oil changes, filter replacements, minor adjustments consuming minimal time and resources. Where British crews spend hours diagnosing and repairing complex failures, American mechanics complete their work in minutes using standardized procedures and interchangeable parts. The comparison reveals uncomfortable truths about industrial philosophy. British tanks feature sophisticated components requiring skilled technicians and specialized tools. American tanks emphasize simplicity and standardization, enabling rapid maintenance by ordinary soldiers with basic training. In field conditions, simplicity trumps sophistication every time. The maintenance logs document this advantage with merciless precision. British morale begins eroding. Cromwell crews take pride in their tank's speed and firepower, but growing mechanical problems undermine confidence. Watching Sherman crews complete daily maintenance in half the time proves demoralizing to soldiers who expected to demonstrate national superiority. Richardson's reports to London grow increasingly pessimistic. The general can no longer dismiss failures as minor teething troubles or isolated manufacturing defects. The pattern is too clear, too consistent, too damaging to ignore. Something fundamental is wrong with the Cromwell's integration of power and reliability. 2 weeks of intensive testing have exposed this flaw with devastating clarity. A simple fuel pump replacement on a Sherman takes 22 minutes. The same operation on a Cromwell consumes 3 hours. The Meteor engine's problems go deeper than simple overheating or excessive wear. By the trial's 11th day, Rolls-Royce engineers identify the core issue. The engine's adaptation from aircraft to ground vehicle was fundamentally flawed. The Merlin aircraft engine, from which the Meteor derives, had been designed for different operating conditions entirely. In aircraft, the engine runs at high power for limited periods with excellent cooling from slipstream airflow. In tanks, it operates continuously at sustained loads with inadequate ventilation and cooling. The difference proves catastrophic. Vibration analysis reveals additional problems. The Meteor's high compression cylinders generate tremendous power, but also produce harmonic vibrations the tank's transmission cannot adequately absorb. Bolts loosen, despite proper torque specifications. Exhaust gaskets fail repeatedly, as vibration breaks their seals. Fan belts stretch and snap under oscillating loads. Rolls-Royce Service Bulletin 43-MT/7 documents these findings with technical honesty. The adaptation of aircraft engines to ground vehicles requires more than simple mounting modifications. Damping systems, cooling capacity, transmission design, all need fundamental revision to match the Meteor's output characteristics. The Cromwell's transmission, designed before the engine's full power became apparent, simply cannot handle sustained torque loads during extended operation. By August 14th, only 14 of 20 Cromwell tanks remain mobile. 6 have suffered failures severe enough to require depot-level repairs, work that cannot be completed in field conditions even with skilled technicians and proper equipment. The trial's midpoint has become a crisis point. What gave the Spitfire its legendary climb rate and combat effectiveness now threatens to immobilize Britain's fastest tank. The same Rolls-Royce engineering philosophy that produced magnificent aircraft engines proves inadequate for ground vehicle applications. Speed and power mean nothing if reliability cannot match operational demands. The Cromwell is failing that fundamental test with each mile traveled. Of 20 Cromwell tanks, only 14 remain mobile by day 10. Richardson's observers conduct detailed comparisons of maintenance procedures, documenting differences that explain the performance gap with painful clarity. U.S. mechanics demonstrate their methods while British teams watch, learning techniques that seem almost impossibly efficient. Parts interchangeability makes the most dramatic difference. American tanks share 90% common components across all Sherman variants. British tanks achieve only 65% interchangeability, with variations between manufacturers creating compatibility problems. A Sherman crew can cannibalize parts from any damaged American tank. Cromwell crews need manufacturer-specific components that might not be available in forward areas. War Office Technical Review number 2279 documents these disparities with statistical precision. Field downtime per tank: Sherman, 1.4 hours daily; Cromwell, 4.9 hours daily. Time required for engine removal: Sherman, 6 hours; Cromwell, 14 hours. Average repair complexity: Sherman maintenance requires basic mechanical skills. Cromwell service demands specialized training and tools. American standardization extends beyond physical components to include procedures and training. Every U.S. mechanic learns identical methods for identical tasks, creating interchangeable personnel to match interchangeable parts. British training varies by regiment and manufacturer, producing skilled individuals but lacking systematic uniformity. The quality control differences reveal fundamental manufacturing philosophy gaps. American production lines maintain rigid tolerances and specifications, rejecting components that deviate even slightly. British factories allow greater variation, trusting skilled fitters to hand-adjust parts during assembly. This craftsmanship approach produces excellent individual tanks, but creates maintenance nightmares when field repairs require exact component matching. By August 20th, the pattern has become undeniable. Britain built speed and sophistication. America built systems and sustainability. Only one approach can support extended combat operations. British crews maintain professional discipline despite growing frustration. They admire the Cromwell's performance when it works properly, appreciating speed and power that makes it exciting to operate. But they increasingly trust the Sherman to complete missions without breakdown or delay a practical concern that outweighs emotional attachment to home-produced equipment. Soldiers need weapons they can rely upon, not tanks that impress during demonstration runs, but fail during sustained operations. Britain built speed. America built systems. Only one survives the test. The convoy completes the loop. Richardson personally reviews final maintenance logs and performance summaries, compiling statistics that will determine British armor procurement for the remainder of the war and beyond. The numbers tell their story without embellishment or interpretation. Cromwell tanks require 0.07 maintenance hours per mile, more than double the Sherman's 0.03 hours per mile. Operational availability. Cromwell 77%, Sherman 94%. Mean distance between breakdowns. Sherman 510 miles, Cromwell 245 miles. Every metric favors the American tank by substantial margins that cannot be dismissed as measurement error or statistical noise. Preliminary field report dated August 25 compiles these findings with clinical detachment. British crews demonstrated excellent tactical skills and proper maintenance procedures. The Cromwell tank achieved impressive performance during limited periods, but sustained endurance under field conditions favors the Sherman by ratios approaching 2-to-1 in critical categories. Richardson's confidential summary to the War Office avoids emotional language or defensive justifications. The data speaks clearly enough without interpretation. British tank design prioritized performance characteristics, speed, firepower, armor, while American design emphasized reliability, maintainability, logistical sustainability. Combat effectiveness requires both performance and reliability, but reliability proves more critical to sustained operations. A tank that reaches 40 miles per hour means nothing if it cannot complete the march. British crews reached their own conclusions independently of official reports. They lived with both tanks for 3 weeks, experiencing the differences firsthand rather than reading statistical summaries. The Cromwell remains popular for its exciting performance and national pride associations. But every crew acknowledges privately that they trust the Sherman more for actual combat operations where mechanical failure could mean death or capture. The contrast between expectation and reality could not be more complete. British officials anticipated data validating continued Cromwell production and reduced dependence on American imports. Instead, they received evidence that American industrial methods produced more reliable equipment despite lower performance specifications. Exercise Dracula concludes with formal ceremonies and official recognition for participating crews. But the real conclusion comes in classified meetings where British officials confront uncomfortable truths about their nation's industrial capabilities and design philosophies. The test meant to prove British supremacy becomes an empirical confession of failure. The classified report Richardson delivers becomes one of the war's most consequential documents, despite remaining sealed for decades. Designated most secret and restricted to senior War Office officials, it compiles Exercise Dracula's findings into tables, charts, analyses that leave no room for alternative interpretations or optimistic reframing. The core statistics appear in stark columns. Reliability ratio: Sherman 2.3 to 1 over Cromwell. Workshop hours per 100 miles: Sherman 3.4, Cromwell 7.9. Spare parts consumption per 1,000 miles. British tanks require 2.1 times more components than American equivalents. Richardson's conclusion avoids political language while delivering unmistakable strategic guidance. In prolonged campaign conditions, he writes, "The Sherman exhibits superior reliability essential for sustained operations." While the Cromwell demonstrates admirable performance characteristics during limited engagements, its mechanical endurance proves inadequate for extended deployment without extensive support infrastructure. The report includes detailed analysis of failure modes and root causes. Meteor engine problems stem from inadequate cooling systems and transmission incompatibility. Clutch failures result from underestimation of torque loads. Gasket problems reflect insufficient vibration damping. Every issue traces to fundamental design decisions made before field testing revealed their operational consequences. The Cromwell was not badly built, it was badly designed for the missions British armor would face. Comparison with American design philosophy fills entire report sections. U.S. tank development prioritized reliability from initial concept stages, accepting performance compromises to ensure mechanical endurance. British development emphasized capability maximization, assuming reliability problems could be resolved through improved maintenance. Exercise Dracula proved American assumptions correct and British assumptions dangerously optimistic. The document remains classified most secret until 1978, 35 years after its writing. But its immediate impact shapes British procurement decisions throughout the war's remainder. Senior officials who read Richardson's analysis understand they face strategic choices between national pride and military effectiveness choices, where only one answer serves the soldiers who will depend on these decisions. War Cabinet discussions during September 1943 reference recent reliability trials, without providing details even to most ministers. Churchill himself reviews the summary findings, recognizing their implications for British armor strength and Allied cooperation. The Prime Minister makes no public comment, but privately supports procurement decisions reflecting Exercise Dracula's lessons. British tank crews continue operating Cromwells throughout the war, particularly in reconnaissance and exploitation roles, where the tank's speed provides genuine advantages. But the Cromwell never becomes the main battle tank British officials had envisioned. That role continues falling to the Sherman. Imported by the thousands under Lend-Lease and operated by British armored divisions through Normandy, France, and into Germany itself. The document remains sealed for 35 years, but its verdict changes British procurement overnight. Investigation traces the Cromwell's reliability problems beyond specific design flaws to reveal systemic differences in British and American manufacturing philosophy. These findings will influence British industrial policy for decades. British tank production during 1943 relies on dispersed manufacturing, Leyland Motors, Birmingham Railway Carriage and Wagon Company, Nuffield Organization, and smaller contractors all contributing components and assemblies. Each facility maintains its own standards, tolerances, quality control procedures. The system preserves traditional craftsman approaches while distributing production across multiple sites to reduce vulnerability to bombing. Ministry of Supply Industrial Review for autumn 1943 documents the costs. Parts from different manufacturers often require hand fitting during assembly, consuming time and skilled labor. Quality variations mean some tanks perform better than others, despite identical designs. Maintenance complications arise when parts from one manufacturer will not fit tanks built by another facility. American industry evolved differently. Centralized Ordnance Department supervision ensures identical specifications across all suppliers. Quality control inspectors reject components that deviate from precise tolerances, even by minimal amounts. Assembly procedures follow detailed technical orders, eliminating craftsman discretion. The result sacrifices individual excellence for collective consistency. Every Sherman meets minimum standards without exception. The production statistics reveal staggering disparities. U.S. facilities manufacture 2,000 Sherman tanks monthly, using assembly line techniques. British plants produce 150 Cromwell tanks monthly, using traditional manufacturing methods. Labor efficiency comparisons prove even more striking. One U.S. tank requires 12,000 man-hours, while Cromwell production consumes 22,000 man-hours per vehicle. The contrast reflects deeper economic and social differences. American industry embraced mass production philosophy during peacetime, developing techniques that transferred directly to military manufacturing. British industry maintained craft traditions that produced excellence but could not scale efficiently to wartime demands. Richardson's analysis includes frank assessment of these limitations. British manufacturing excellence is undisputed. He writes, But excellence alone cannot supply the armored formations required for modern warfare. Quantity and consistency have become prerequisites for military effectiveness. For British officials reading these words, the implications extend far beyond tank production. If traditional manufacturing cannot compete with American mass production in armor, similar gaps likely exist across military industries. The nation that pioneered the Industrial Revolution now finds itself outproduced by its former colony. The historical irony is not lost on senior officers who understand both military and industrial history. Britain taught the world factory production during the 19th century. America perfected those lessons during the 20th. For every British tank completed during August 1943, 13 American tanks roll off production lines. That arithmetic dictates strategic realities more certainly than any battlefield engagement or tactical innovation can alter. The Sherman is born from industry, the Cromwell from craftsmanship. In total war, craftsmanship cannot compete. November 1943, General Staff Committee, London, Whitehall. The meeting marks formal conclusion of Exercise Dracula's immediate impact on British procurement. Senior officers review Richardson's conclusions and supporting documentation, then make decisions governing British armor deployment through the war's conclusion and beyond. The discussion avoids emotional arguments about national prestige or engineering pride. Facts dominate deliberation: maintenance ratios, operational availability percentages, spare parts consumption rates. Staff officers recognize that soldiers' lives depend on equipment reliability, not patriotic sentiment. Richardson's memorandum to the committee captures the essential logic. Future armored strength, he writes, shall depend upon those machines capable of fighting, not merely running. Operational reliability has proven the decisive factor in sustained campaigns, outweighing advantages in speed or firepower that cannot be maintained under field conditions. The operational consequences follow directly. British armored divisions will continue receiving and operating M4 Sherman tanks as their primary battle equipment through Normandy, France, and the final advance into Germany. Cromwell production will continue, but at reduced rates, with these tanks assigned primarily to reconnaissance and exploitation roles, where their speed provides genuine advantages and mechanical support can be more readily available. This decision avoids dramatic announcements or public admissions of British industrial limitations. Official statements emphasize complementary capabilities and optimized deployment, rather than acknowledging that American tanks proved more reliable than home-produced alternatives. Political sensitivity requires diplomatic language, but military planning reflects harder truths that Exercise Dracula revealed. British tank crews experience these decisions as gradual changes rather than sudden reversals. Sherman deliveries increase while Cromwell allocation shifts towards specialized units. Maintenance logistics simplifies as standardized American parts become more readily available. Training emphasizes Sherman operations, since these tanks will equip the majority of combat formations. The strategic impact extends beyond immediate procurement. British planning for the Normandy invasion and subsequent campaigns assumes Sherman reliability when calculating maintenance requirements, spare parts allocation, operational tempo. The confidence that these tanks will perform as expected, based directly on Exercise Dracula's data, enables more aggressive operational planning than would have been possible with less reliable equipment. Historical perspective reveals Exercise Dracula as a pivotal moment when British military leadership chose effectiveness over prestige. The decision to continue dependence on American tanks represented mature strategic thinking that prioritized winning the war over maintaining appearances. The verdict, documented in Richardson's November memorandum, quietly ends one chapter of British tank development while opening another. The Cromwell represented Britain's attempt to create a world-class battle tank using traditional design and manufacturing approaches. Its relative failure during Exercise Dracula demonstrated that modern warfare required different methods Britain would need to develop to remain militarily competitive in the post-war era. That development would take years and require substantial industrial reform. But the seeds planted during those 2,000 miles across England would eventually produce the Centurion, a tank designed from the beginning for reliability, maintainability, sustained operational effectiveness. Future armored strength shall depend upon those machines capable of fighting, not merely running. Technical lessons from Exercise Dracula influence British tank development throughout the war's final years and into the post-war period. Engineers study Richardson's data carefully, identifying specific improvements that can address the Cromwell's documented failures. Work on the Comet begins in late 1943, incorporating Exercise Dracula's findings into refined design. The Meteor engine remains but is derated from 600 to 570 horsepower, reducing power output to levels the transmission can reliably handle. The gearbox receives complete redesign with improved cooling systems and stronger components capable of sustained operation under field conditions. Modular access panels simplify maintenance, allowing crews to reach critical components without extensive disassembly. Tank Board Proceedings Number 1147 from 1944 documents these modifications with detailed technical drawings and performance specifications. Every change traces directly to failures documented during the original trial. Overheating problems addressed through enhanced cooling, vibration issues resolved with improved mounting systems, maintenance complications eliminated through better component accessibility. The Centurion program absorbs even more comprehensive lessons. Development begins in 1943, with requirements emphasizing reliability and maintainability as primary design criteria rather than afterthoughts to performance specifications. Engineers design maintenance procedures before finalizing mechanical systems, ensuring that servicing will be practical under field conditions. Component standardization receives priority from initial design stages, with interchangeability requirements built into procurement contracts. These programs reveal how failure can drive improvement more effectively than success. The Cromwell's problems exposed gaps in British design philosophy and manufacturing practice, forcing systematic re-evaluation of approaches that seemed adequate before Exercise Dracula's data provided objective evidence. The transition from Cromwell to Centurion represents evolution rather than abandonment. British engineers retain the Meteor engine but learn to integrate it properly with supporting systems. They maintain emphasis on firepower and protection while adding American-style attention to reliability and maintenance. The synthesis combines best elements of both approaches, creating tanks that can match performance with endurance. Post-war evaluation confirms these improvements' effectiveness. The Centurion achieves operational availability rates exceeding 90% during extended deployments, matching or surpassing Sherman reliability while providing superior firepower and protection. The tank serves British and Allied forces for decades, becoming one of history's most successful armored vehicle designs. The contrast could not be more complete. The Cromwell failed Exercise Dracula by prioritizing performance over reliability. The Centurion succeeded in subsequent decades by balancing both requirements from the beginning. British engineering learned its lesson. Mechanical excellence means nothing without operational endurance, and prestige counts for nothing beside practical effectiveness in sustained combat. The Cromwell stumbled so that the Centurion could endure. The final chapter of Exercise Dracula's story begins when Richardson's most secret report finally receives declassification and public release. Historians examining the document discover evidence of a trial that fundamentally shaped Allied armor operations during World War II's final years, yet remained almost entirely unknown outside classified military archives. The numbers that shocked War Office officials in 1943 still impress military analysts 3 decades later. The reliability ratios, maintenance disparities, operational availability gaps, documented systematic American advantages that helped explain Allied victories during subsequent campaigns. Sherman reliability enabled rapid advances across France, maintaining operational tempo that German forces could not match with their more sophisticated but less reliable armor. Bovington Tank Museum receives the declassified documents and incorporates them into exhibits examining wartime tank development. The archive's summary captures Exercise Dracula's essential lesson in a single sentence: the Cromwell was faster. The Sherman, however, always arrived. That phrase becomes shorthand for understanding the trial's significance. Speed and power mean nothing if mechanical failures prevent reaching objectives. Reliability trumps capability when sustained operations demand that equipment function day after day without breakdown or extensive maintenance. The Sherman's modest performance specifications concealed its decisive advantage. It worked consistently under operational conditions that defeated more impressive but less reliable alternatives. Historical analysis reveals Exercise Dracula's broader significance beyond immediate procurement decisions. The trial demonstrated how objective testing could overcome institutional bias and national pride, forcing practical choices based on evidence rather than preference. Richardson's willingness to report unfavorable findings honestly, and British leadership's acceptance of those findings, despite their implications, represented mature, strategic thinking that contributed to eventual Allied victory. The lessons influence modern armored doctrine worldwide. Military planners studying Exercise Dracula recognize that reliability and maintainability must be design priorities from initial concept stages, not problems addressed after performance specifications are finalized. NATO standardization agreements incorporate these principles, establishing common maintenance procedures and parts interchangeability requirements across Allied forces. Educational programs preserve Exercise Dracula's technical lessons for subsequent generations. British armor schools teach maintenance procedures using case studies from Richardson's report, demonstrating how complex systems can fail despite sophisticated engineering. American armor courses use the trial as example of how standardization and industrial discipline can create decisive operational advantages. Survivor Cromwell tanks in museums today bear plaques explaining Exercise Dracula and its impact on British armor development. Visitors can examine the Meteor engine and see the powerful but problematic system that performed impressively during short demonstrations but failed during sustained operations. The contrast with preserved Sherman tanks, with their simpler, more reliable Continental engines, provides tangible evidence of the design philosophy differences that Richardson's report documented with devastating clarity. The classified report that shaped British procurement for years finally enters public historical record, ensuring that lessons learned during Exercise Dracula inform future military planning and equipment development. The trial's significance extends far beyond the specific tanks tested during summer 1943, establishing principles about reliability, maintainability, industrial capacity that remain relevant to modern military forces operating complex equipment under demanding conditions. If you value documentary military history, built on verified archival research and detailed technical analysis, consider supporting this work. Your engagement helps preserve factual accounts of the engineering decisions, industrial capabilities, operational realities that determined warfare's outcome. These stories honor the soldiers, mechanics, engineers whose work shaped history, ensuring their contributions remain documented for future generations who study how industrial democracy defeated totalitarian aggression. The morning of August 3, 1943, marked a turning point that neither British nor American observers fully recognized at the time. British commanders authorized Exercise Dracula, expecting validation of national engineering superiority. American liaison officers prepared to document their tanks competing against newer, faster British designs. The outcome, 77%, British operational availability versus 94% American reliability, demonstrated how industrial philosophy could decisively outweigh performance specifications. Numbers tell transformation stories more clearly than prose ever could. Before Exercise Dracula, British confidence in the Cromwell remained unshaken despite scattered reliability concerns. After 2,000 miles of documented comparison, mathematical certainty replaced optimistic assumptions. The maintenance hour ratios, breakdown frequency data, spare parts consumption statistics created evidence impossible to dismiss or reinterpret. American standardization defeated British craftsmanship through systematic industrial discipline applied across entire production systems. Human consequences proved equally significant. British soldiers who would operate Sherman tanks during subsequent campaigns received reliable equipment rather than impressive but fragile alternatives. Equipment failures during combat operations meant death or capture, not merely inconvenience or delay. Richardson's decision to recommend continued Sherman deployment may have saved thousands of British lives by ensuring soldiers received reliable equipment. Industrial comparisons revealed fundamental strategic imbalances extending beyond tank production. American factories manufactured thousands of Sherman tanks monthly, while simultaneously producing aircraft, artillery, ammunition in quantities British industry could not match. Superior industrial capacity translated directly into tactical advantages across every military domain. Scientific achievement established new paradigms for military procurement that would influence defense planning for decades. Exercise Dracula demonstrated that objective testing could identify equipment shortcomings before combat revealed them through casualties and mission failures. The trial's methodology controlled comparison, comprehensive data collection, honest reporting, became template for subsequent evaluation programs across Allied forces and, eventually, NATO standardization procedures. Strategic implications extended beyond immediate tactical results. British acceptance of American equipment superiority, documented through Richardson's trial, strengthened Allied cooperation and enabled more effective resource allocation. Rather than wasting limited industrial capacity attempting to match American tank production, Britain could focus resources on areas where its capabilities provided unique contributions. The partnership benefited from honest assessment of comparative advantages, rather than prideful insistence on self-sufficiency, regardless of cost or effectiveness. Exercise Dracula's principles guided post-war military development across Western nations. Reliability testing became mandatory for new equipment programs. Maintenance procedures received design priority equal to performance specifications. Standardization displaced traditional approaches, emphasizing individual excellence over collective consistency. Modern armies operate on assumptions that Richardson's trial helped establish that equipment must work reliably under sustained operational stress, that maintenance simplicity determines combat readiness more than peak performance, that industrial capacity enables military capability. Today, defense analysts studying armored vehicle procurement still reference Exercise Dracula when evaluating competing designs. The trial's lessons remain relevant despite 7 decades of technological advancement. Sophisticated electronics and complex systems can fail as catastrophically as Meteor engines overheated during summer 1943. Standardization and maintainability still determine whether impressive specifications translate into operational effectiveness. The fundamental questions Richardson answered: can it finish the march? Can crews maintain it? Will it work tomorrow and next week and next month? Still dominate procurement decisions for modern militaries, operating equipment far more complex than any tank conceived during World War II. The Bovington Tank Museum preserves Exercise Dracula's physical legacy. Cromwell tanks sit beside Sherman tanks in climate-controlled halls, their mechanical differences visible to informed observers. The Meteor engine's impressive specifications contrast with the Continental radial's modest performance yet historical plaques, explain why modest reliability defeated impressive capability. Visitors can examine the gearbox components that failed during the trial, understanding how sophisticated engineering proved inadequate without matching attention to sustained durability. Richardson's report, now fully declassified and available to researchers, stands as historical testament to intellectual honesty and professional integrity. The general could have minimized British shortcomings, emphasized Cromwell advantages, or recommended continued production despite evidence of mechanical inadequacy. Instead, he documented reality with clinical precision and recommended procurement decisions based on soldiers' needs rather than national pride. That choice exemplified the professional military judgment that helped Allied forces achieve victory despite facing enemies with superior tactical doctrine and battlefield experience. The Cromwell's fate reflected broader patterns in 20th century military history. Nations that prioritized prestige over practicality, sophistication over sustainability, tended towards strategic failure regardless of tactical brilliance. Nations that accepted hard truths revealed by objective testing, that chose effectiveness over pride, achieved sustainable military capabilities supporting long-term strategic success. Exercise. Dracula demonstrated these principles in miniature 2,000 miles that revealed fundamental truths about industrial warfare's requirements. British tank crews who operated both Cromwell and Sherman tanks during the war's final years understood these lessons through direct experience. They appreciated the Cromwell's exciting performance during short engagements, but trusted the Sherman to complete extended operations without mechanical drama. Their practical wisdom, born from maintaining equipment under field conditions, validated Richardson's statistical analysis through lived experience. The tank that always arrived proved more valuable than the tank that sometimes impressed. On August 25, 1943, Richardson compiled the final data that would transform British armor procurement. 120 Cromwell and Sherman tanks had completed 2,000 miles across English roads and fields. The maintenance logs, breakdown reports, performance statistics told an unambiguous story about reliability, sustainability, the industrial philosophies that produced them. The numbers spoke clearly to anyone willing to listen without prejudice or preconception. 82% of Cromwell tanks suffered significant mechanical problems during the trial, failures serious enough to require depot-level repair or extensive field maintenance consuming days rather than hours. 17% of Sherman tanks experienced similar difficulties, a reliability advantage approaching 5-1 in favor of American design and manufacturing. British engineering had produced impressive performance. American industry had created sustainable capability. Only one approach could support armies advancing across Europe, and Exercise Dracula's data proved which philosophy would prevail. The morning mist at Bovington on August 3 had concealed the trial's ultimate significance. British confidence and American pragmatism both seemed reasonable positions at the journey's beginning. 2,000 miles later, mathematics had settled debates that pride and tradition could not resolve. The Cromwell was faster, but the Sherman always arrived. That simple truth, documented through countless maintenance hours and breakdown statistics, shaped British armor operations through victory in Europe and influenced military procurement principles that endure to the present day. Exercise Dracula became a cautionary legend in military circles, proof that engineering pride can lose to industrial discipline, that sophisticated systems can fail against reliable simplicity, that objective testing serves soldiers better than optimistic assumptions. The trial's lessons cost Britain prestige, but saved British lives, trading national pride for operational effectiveness in the war that would determine whether democracy or tyranny governed Europe's future. The 2,000-mile journey across wartime England demonstrated truths that generals and politicians needed to understand but often resisted accepting. Superior equipment determines battles. Superior industry determines wars. Clever engineering impresses observers. Reliable manufacturing supports armies. Performance specifications fill brochures. Maintenance statistics predict victory. Richardson's report converted these abstractions into concrete evidence that could not be dismissed or rationalized away. On August 25, 1943, 82% of Germany's expectations about British tank superiority were destroyed in a single classified report, not by enemy action, but by the silent work of American industrial discipline that British officials never fully understood until the numbers made denial impossible.